Okay, here we go into the second video in our lesson on how to integrate when e to the x is involved. In this video, we're going to go over a couple of manipulation / more challenging e to the x problems to start, and then we're going to go over some definite integrals involving e to the x. None of this will be too crazy for you, I promise. We've actually looked at antidifferentiation like this in the past. Let's jump into it. So, when you've got a problem like this, the antiderivative of e to the 3x minus 2e to the x plus 5 all over e to the x, we notice that e to the x could actually be divided into each of these terms. So I view it like this: e to the 3x over e to the x minus 2e to the x all over e to the x plus 5 all over e to the x. Now 5 over e to the x, I'll just leave it like that just for now. And that's all dx. So now I'm essentially going to simplify this and set myself up for antidifferentiation. So any base that's the same, when you have the same bases and you divide them, you subtract the exponents. So you'd have e to the 3x minus x, which is 2x. Then you got your minus here. The same number divided by the same number, well, that's just going to be 1, so you're going to be left with 2. This is going to be 5e to the minus x. The reason why I write it like that is because that is easier to antidifferentiate than this. You wouldn't want to take this and say, oh, it's the log of e to x. It's not. Right? It's not 1 over x. It's 1 over e to the x. Very, very different. Okay, now from here we'll antidifferentiate each part. Well, I'm going to do this without u substitution now. I'm going to show you how to do that so you don't have to u sub this and this, because it's simple enough, I think, to do a forwards-backwards type of thinking. Let me show you what I mean. We know the antiderivative of e to the 2x is going to involve e to the 2x, because the derivative of e to the 2x is e to the 2x times 2. Well, there's no 2 there. So there would be a 2 if I took the derivative of this, so I have to cancel out the 2 that would come out. So that would be e to the 2x times 1/2. The derivative of that would be e to the 2x times 2. The 1/2 cancels that out and leaves us back here. So see how I'm taking a derivative to actually do the antiderivative. I'm saying the derivative of what gets me here. Minus, well, 2 is just 2x. I'm going to do something similar here with 5e to the minus x. So that's going to be plus 5. We know that the derivative of e to the minus x is e to the minus x times negative 1. But that's not negative, so I'll put a negative here so that when I do the times negative 1 times the negative 5, that'll give me positive 5. And of course you have plus c. Now you could write that as minus 5e to the minus x. I'm just going to leave it like that. Not bad, right? Not bad at all. Okay, this one, what do we do? Well, I let u equal to the denominator because its derivative is going to involve e to the minus x. So it's a sneaky u substitution problem. U equals 6 plus e to the minus x. The derivative, you got this, is du equals, that's 0, e to the stuff, d stuff, so it's times negative 1, dx, which is the same as minus e to the minus x dx. Now we don't have a minus, so I'm going to put that in there and also on the outside to equal things out, just like a normal u sub, and now I've got du. Oh, that's very nice indeed. So now I have du over u. Ooh, 1 over u, that's the ln. So that's going to be minus ln of the absolute value of 6 plus e to the minus x. And you might be, wait, 6 to the e plus x, where did I get that from? It's minus ln of u, the absolute value of u. Now, if you got one of those teachers that's like, only use the absolute value where necessary, e to the minus x is always positive. 6 plus a positive number is always positive. So technically, you only need parentheses to group things. You don't need the absolute value, technically. All right, not so bad. So what we have going on the second half of the video here is definite integrals with e. It's not that bad. Okay, so I'm going to use u sub with each of these. Even though you technically don't have to, I'm going to. So u substitution, we'll use the upper bound there. Not upper bound, we'll use the exponent. U equals 10 minus x. Du is equal to minus 1 dx. Well, we don't have a minus 1 dx, so I'll put in a minus and a minus. That gives me the minus 1 dx that I need. Okay, so I've got the minus out there. Minus 1 dx is du. That leaves me with e to the u. But now we need to sub in for our x values, right? So when x is equal to negative 1, u is equal to 10 minus a negative 1, using this to calculate our x value into a u value, and that's 11. And then we'll go at it with 2. So when x equals 2, u equals 10 minus 2, using this again, is equal to 8. Okay. So now from here, I know we don't love the higher number and the lower number. It's fine however you want to do this out. If you happen to notice this, you could flip the sign and do 8 to 11, right? You totally could. I'm going to leave it like this just so that we don't funkify this any further. But you could do what I just noticed out loud. So that's minus e to the u. The antiderivative e to the u is just e to the u, evaluated from 11 to 8. Okay, so that's going to be minus e to the 8. That minus is from the fundamental theorem of calculus. This minus is from the actual function. And so now what we're left with is minus e to the 8 plus e to the 11th, or e to the 11th minus e to the 8. Awesome. All right, you ready for the next one? Of course you are. Let's go. So with this particular problem, the innermost function, if we let that equal u, we notice its derivative is right out here. Let's do that. U is equal to e to the x. Du is therefore equal to e to the x dx. Okay, so now from here, I've got an exact du going on right there. So I've got the antiderivative. We're going to have to adjust our x values like always. But I've got du. And I've got the sine of u happening right there. Okay, so now when x is equal to 0, u is equal to e to the 0, which is equal to 1. Not bad. Check out this next one. I love this next part. It was fun making this problem. When x equals ln of pi over 4, which you might have been looking at first and been like, what is that grossness? Ln of pi over 4. Well, we're going to plug that in. You've got u is e to the x. So e to the ln of pi over 4. E to the ln undoes each other, and we're left with pi over 4 is u. And that's not such a bad thing. Now, the sine of 1 is going to be a pretty gnarly thing, right? That's going to be pretty gross. We will deal with that when we get there. The antiderivative of sine of u is minus cosine of u, because the derivative of minus cosine is positive sine. And that'll be evaluated from 1 to pi over 4. Not bad. Let's finish it out in style. So this is going to be minus cosine of pi over 4. Minus, that's from the fundamental theorem. Minus, the second minus is from the actual function, cosine of 1. And so that's going to be minus root 2 over 2. Minus a minus is plus whatever the cosine of 1 is. We'll leave it. And as a reminder, on the A, B, or BC exam, you can leave your answer here or here, as long as it's numerical and the numbers have been evaluated. You can't leave it here. You got to evaluate things. All right, we're going to leave it here on this video. I can't wait to see you in the exercises for this section. I'll see you there. Peace.